Hello, this is Chris Rossi from Dusky Electronics, and today we're filming our first episode. Us, like there's other people here. It's me. It's just me. I'm all by myself. I'm all alone right here. But anyway, it's our first episode of Seldom Asked Questions here at Dusky Electronics. Today's question comes to us from no one, who asks, what exactly is going on with an Octomotron Fuzz? What does that thing do? Well, I'm glad you asked. It turns out that it's kind of a different kind of circuit from a lot of things called fuzz. And let's talk about the reason for that a little bit. What is fuzz anyway? It turns out fuzz is not a single thing. When did we start getting an effect called fuzz? Well, that was around the 60s or so, when companies first started making pedals and little devices. I believe Maestro by Gibson was the first one, and they called it just the Maestro Fuzz, I think. It was called the Fuzz. And anyway, so henceforth everybody called, basically around that time, everybody who made a box that was designed to distort a guitar signal called it a fuzz. And it turns out that there are a lot of different ways you can distort a guitar signal. So calling something a fuzz doesn't necessarily tell you much about what it actually does or how it works. Sort of the constant from this time period is that people were just making stuff that mangled the signal in some way that they found interesting. What comes a little after that is people start realizing, or at some point the belief becomes commonly held that the ultimate in guitar distortion is an overdriven tube amp. And so people start making devices to simulate the sound of overdriven tubes, and these often get called overdrives or distortion pedals, things like that. Again, there's no real hard and fast rule. There's no one way to build an overdrive pedal. There's no hard and fast definition of what is an overdrive pedal versus what is a distortion pedal versus what is a fuzz pedal. Basically, they're all distortion pedals. And the things that get called fuzz tend to harken back to sounds and circuits stemming from the 60s that were designed without any regard towards simulating a particular sound somebody had heard before. So they weren't trying to reproduce the sound of an overdriven tube guitar amplifier. A really good way to produce the sound of an overdriven tube guitar amplifier is to plug into a tube guitar amplifier and turn it up. So these fuzz pedals do something different. So getting back to the Octomotron, what is the Octomotron? The Octomotron is my take on a type of fuzz called an Octave Fuzz. What is an Octave Fuzz? Well, I guess sometime in the late 60s, some guy made a buzz box called the Octavia. Jimi Hendrix used this pedal. It used a transformer and some diodes to basically rectify the audio signal. And that's a really strange thing to do. What does it mean to rectify an audio signal? Well, a rectifier in electronics is basically a device that takes alternating current like this, and alternating current, it goes back and forth, but if you look at it on an oscilloscope, you can visualize it as a wave that goes up and down like this. And what a rectifier does is basically it stops current from going back one direction. So current only flows one direction. And if you're looking at it on an oscilloscope, you know, your wave only goes up. It doesn't go down, it only goes up. And you can have a half wave rectifier or a full wave rectifier. The Octavia and the Octomotron pedals are full wave rectifiers, which means that the part of the wave that would be down going is flipped up, so that it is in fact upgoing. And so if you have a wave that goes like this, instead it goes like this. And one thing that tends to do is basically effectively doubles the effective frequency of the signal, which if you double the frequency of something, that's the same as increasing its pitch by 1 octave, so it's an octave fuzz. Also, as you can imagine, a wave that's been flipped up in that way is gonna sound really different from how it would normally sound, because it's a very strange thing to do to an audio signal. And the cool things about fuzzes is that they're very strange, and they do strange things, and we love them for that. Now, most fuzzes work on a completely different principle. But you know, why should I tell you when I can show you? So let us direct our gaze, for now, at the oscilloscope. Now, what do we have here? This yellow trace you see at the top is an input signal. This is a sine wave that is oscillating at 440 Hertz, which is the pitch, which is the frequency of an A note, concert A. That is the top trace. The bottom trace is the output of the Octomotron Fuzz. You can see it looks pretty different from the input. I'm going to turn the input down. Actually, let's turn the input all the way down, and then we'll bring it up slowly. What do we see? We see that where we have a sine wave on top, we have kind of a little humpity hump thing on the bottom. That's pretty different. You can see that basically the humpity humps are always going up. The bottom half of the would-be waveform is, instead of going down, is flipped up. And of course there are other strange things going on in here, because it's, you know, there's extra gain, and so it's kind of distorting the signal a little bit before it even gets rectified in that way, because we're overdriving some of the internal circuitry. You can sort of see more of that or less of that as you turn the input signal up and down. You can see it does really strange things. You get to right around here, you get a little nipple there on those guys, and you know, that's pretty weird. You can see that the humps are different heights. Why is that? Well, that's actually a little bit by design. I have the diodes that do the rectifying in this thing are germanium. Use germanium diodes because they have a fairly low forward voltage, which makes them well suited to this application. Germanium, solid state devices made out of germanium tend to be pretty squirrely. There tends to be a lot of variation from device to device and how they respond. And what I found in trial and error, because of that, I have to actually audition every single diode that I put in my Octomotron Fuzz pedals. You know, so it means I sit here with an oscilloscope and listening, and I sit there and I try every single germanium diode that goes into an Octomotron, and I pick them out. I pick out the good ones. And one thing I have learned to look for, because it sounds kind of cool, is if they're a little bit mismatched. And you can tell they're mismatched because you have one hump that's taller than the other. And when you get a little bit of that mismatch, it just sounds a little more harmonically interesting to me. So I shoot for that. Not sure why, not entirely sure why there's that little nipple there, but I have a theory about it. I think it has to do with, not that most of you care or even would understand, but you know, the classic Octave Fuzz pedal used by Hendrix et al., that is sort of the archetype of this type of effect, used a transformer to basically get copies of the signal that are out of phase with each other, so that you can, which is sort of the first step to making a full wave rectifier, with the diodes then being the second step. The Octomotron instead uses just uses a JFET, which is set up as a split load phase inverter. It's a different way to do that. I think when you overdrive it, if you overdrive that FET all the way into cutoff, you wind up, once that FET cuts off, there's internal negative feedback that stops happening because it can't move anymore, and so that you get a little increase in gain. So that nipple is this increase in gain that happens when the FET cuts off, I'm pretty sure. But kind of the awesome thing, like a really cool thing about doing analog circuit design, is that very simple analog circuits can have very complex behaviors, which is pretty different from, say, doing something in the digital realm where, you know, simple programs will always have simple behaviors, and if you want complex behavior out of something, you have to write a complex program. Just in the analog world, just by virtue of, you know, what happens is the result of a physical process, you know, by these physical devices, you can create a fairly simple circuit that has complicated behaviors, and that's what's cool. That's why tube amps are cool. That's why fuzz boxes are cool. That's why a lot of this stuff just ends up being cool, because the technology itself lends itself to being to having complex behaviors that end up being interesting musically. So that basically is what the Octomotron does, is it rectifies the signal. You can see it on there. We can I'll let you hear a little bit of the sine wave, so I'm going to turn it off. Alright, this is not going to sound pretty because it's just a sine wave, but here's the clean sine wave, unaffected. Now, here it is with the Octomotron engaged. That's way more annoying, isn't it? Alright, let's get some guitar in there. So, that's clean. You can see, and actually what I'm going to do, I'm going to turn off this input signal so that you can see the affected signal that much better. Let's see here. So that's what it, now you've seen what it looks like and you've heard what it sounds like. Now I was trying to say it towards the beginning of this before I got all long-winded on you, and I apologize for that. I didn't realize I was going to get this long-winded. I'm sure you didn't either. But trying to say that an octave fuzz is really like a completely different kind of fuzz from other kinds of fuzzes. And you can imagine like the whole thing where you're rectifying the audio signal, that's a weird thing to do. Most fuzz boxes do not do that. There are a few fuzzes out there that are specifically octave fuzzes. Catalan Bread makes one. There's the Octavia, obviously. I make this one. I think Voodoo makes one. Anyway, you know, there are a few out there, but in the vast, vast world of fuzz, most fuzzes are not octave fuzzes. And in fact, octave fuzzes are so different from other fuzzes, I kind of wish they had a different name. Because what happens is because these types of effects all have the same name, they end up in like roundups with each other. So you'll have like a fuzz roundup that will have 6 variations on like a fuzz face circuit and then like 1 octave fuzz. And you know, the reviewer naturally is approaching them as though they're all very different kinds of apples. You know, and you might go, yes, well, you know, I like the Granny Smith apple. It's a, you know, and then it's kind of tart, and the Pink Lady is has more sweetness to it, or whatever. And it's kind of what people do with the different fuzzes. You know, but then you get to the octave fuzz in the batch, and it's not an apple. It's an orange. You know, it's just a completely different thing. So let's look at that. I happen to have here basically a fuzz face that I made, and this is just a straight up copy of old school fuzz face circuit. I bought some germanium transistors and put it together. I haven't. There's nothing dusky about this thing. I haven't like designed, you know, tweaked it or added any of my own twist or design or whatever. It's basically just the straight up classic circuit. All I really did is I had a handful of germanium transistors, so I did some auditioning of the transistors way back when I was building it to you know, get a combination of transistors that I thought sounded good. But let's cast our gaze once again back to the oscilloscope, and you can see this is our clean input signal. What does a fuzz? You've seen what the Octomotron does to that. Just to remind you, here it is again. Okay, it's pretty crazy. Now, what does a fuzz face do to that? Well, that looks completely different, doesn't it? Well, what's going on here? That basically is a square wave. You can see that there's the duty cycle is skewed a little bit, which, you know, don't worry about what that means. That means the top part is skinnier than the bottom part. You know, basically what a fuzz face is and what it does and what all of the variants, all the fuzz face variants that are on the market today, which there has to be like hundreds of these things, is basically a little transistor amp that has too much gain. And it has so much gain that it's just, you give it a reasonably sized guitar signal and it tries to reproduce it and it can't, because it just, you know, the power supply can only go, you can only go so far with a 9-volt power supply, and it ends up overdriving the internal circuitry and distorting, and we happen to think that sounds cool. Fuzz faces are known for cleaning up when you turn down the gain. Let's see if we can turn down the see here I'm turning down the input signal. You can see that the shape of the wave is changing, but the size really isn't, and that's because there's so much gain in this thing that it's basically, the output is maxed out. Like, it's just hitting the supply rails and it can't go any further than that. But eventually, if we turn it down enough, we should be able to get something that starts to look like a sine wave again. Maybe we can do that. Yep, there we go. So fuzz faces are famous where you can turn down the volume on your guitar and kind of clean it up a little bit. And that's, here you can see that in action. You can actually see what's going on. And that's just because it actually is just a little, like, the amplifier itself in there is pretty linear-ish. Like it's not designed to be a distorting amplifier per se. It's just that it has so much gain that it can't keep up, and so it distorts. But if you just turn down, if you turn down your guitar or just play very light, so it has less signal, then you can actually stay within the headroom of the pedal, and it can, and it cleans up. And that's famous. It's famous for cleaning up. It has a very hard knee from clean to distorted. You can see that it, here we're kind of clean, and then it's all full on into distortion. And what does that sound like? Let's get rid of this sine wave. Turn the guitar back on. So you can see with the guitar volume down, it kind of cleans up. Compare and contrast again with the Octomotron. Alright, I think I have rambled for quite long enough. This has been the first installment of Seldom Asked Questions. If you like this, let me know. Maybe I'll do another one. I don't know. Let me know what you think. Thanks.